So let's get started. So the lecture that I'm going to cover today is root locus
Good
and
morning, sir.
yeah, Lucas, right?
Yes.
Okay. So before we begin, I'd like to show the content of the lecture today. So there are two main parts. First, introduction of the root locus, to talk about what it is and how we can find root locus, and then we will be discussing about rules for sketching root locus. So the first part of this lecture is about a closed loop transfer function and characteristic equation. So first, let me show you a feedback system, a feedback control system represented by block diagram like this. So you have a plan, okay, with transfer function g of s, and output of the plan is c of s, right? Then you design a feedback control by, so you have a reference or desired. Here all s come from the word reference or desired, and then you measure the output of the system to compare with the reference, right? So suppose you have a unit feedback, okay, then you compare with the reference, you have error, and from the information of the error you design a controller, and let's call it just again k, right? And then the controller send the signal to a driver of the system, for example. Then the system start operation. So this one is called controller, okay, and the job is to find what the value of k is such that you can have the error tend to 0, which means you have the output approach to your desired, okay. And one method to design controller to find the controller k is called root locus. But before that, let's see the characteristic equation of the closed loop transfer function. So first you need to find closed loop transfer function. So let me remind again, open loop transfer function is the plan itself, g of s equal to a rational function, okay, n of s over d of s. N means numerator and d means denominator. So the closed loop transfer function would be, okay, closed loop transfer function. Actually, it is the ratio between the output and the reference, which means cs over r of s, and it is denoted by g close, means closed loop, so equal to You still remember from the exercise in the previous lecture. So the closed loop transfer function take this form. Okay. And if we want to use NF and DS, we can rewrite it as K n of S over D of S plus K n of S. So to analyze the system behavior, specifically the stability that you just learned in the previous lecture, in order to have a system stable, we must have all poles located on the left hand side of the complex plane, right? So what is the meaning of poles? Poles is obtained from the characteristic equation. So the closed loop characteristic equation is 1 plus k g of s equal to 0, which means uh, all all the roots that make the denominator of the closed loop transfer function goes to 0 is called poles of the closed loop transfer function. Okay, so all the s that make this that satisfy this equation is called poles. So more generally, we can say d of s plus k n of s equal to 0, right? So this will be used very often. Again, let me recall what is the objective of uh, controller design, the objective that we want to, no, the goal we want. So the goal is to choose the right k such that error tend to 0. Okay, so now we have characteristic equation in this form and k appear in here. So the next step is to analyze what happened with the poles when k varies, right? Anyway, all s that satisfy these equations that we call poles, and if all the poles located on the left half plane of a complex plane, okay, real imaginary. So if pole located on this left half plane, then the system is stable. Okay. Yeah. So what is root locus? So root locus is all values of s that satisfy the system characteristic equation. Okay. So I write down here. Oops. Root locus is all value of s that satisfy the system characteristic equation, which is 1 plus k g of s equal to 0, or d of s plus k n of s equal to 0. And with the vary with the varying value of k. Okay, so as the loop gain k vary from 0 to infinity. Okay, um, to better explain in to better explain this concept, let me illustrate the Locus for you. Um, Imagine that first you pick the value of k as 0. Okay, if k is 0, which this equation reduced to d of s equal to 0, which is the pole of the open loop transfer function, right? Because open loop equal to n of s over d of s. So if k equal to 0, d equal to 0 means uh, the s that satisfy df equal to 0 is the pole of this g of s. And let's say, so you can plot, let's say the pole are all real numbers, so you just illustrate the poles like this, and then if you choose another k, okay, if you choose another value of k, then which is not 0, then you have this equation and you find the new set of s. So you may get another value of yet another set of poles, probably can be here or here. Okay, and you you vary k, yeah, you increase k more and more, and then you may get another pole here, 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 like this. So you have sets of poles with respect to uh, the value k taking in this interval. Okay? And if you just draw to see the evolution of the poles when k increase, you end up something like this, and this called Locus. Okay? All right. So next, let's see an example. Um, let's see example that you have open loop transfer function g of s equal to, yes, just say 0.3 over s plus 2. So again, you have feedback control like this. So you have controller k, and you have the plane g of s, okay, the plan, and then you got output c of s, and feedback like this. So then we can easily find the Laplace transform of the error itself. Yeah, you still remember? Yes. So, well, we have closed loop transfer function g close equal to k g of s over 1 plus k g of s, and this one is actually the ratio between the output and the reference, right? So for the error, maybe I should copy this one. Okay, so for the error here, so the error E of s equal to R of s minus C of s, and C of s actually G close time R of s, right? So here R of s minus uh, kg of s over 1 plus kg of s time R of s. So you have error E of s equal to R of s time this one become just 1 over 1 plus k g of s, right? And if we substitute g of s by the ratio of n over d, I can have, so I can have R of s time d of s. Am I right? Let me check. E1 minus this plus d minus this. Yes, that's correct. And so what I have here, n over d, so I would have, okay, so I would have d of s over d of s plus k n of s. Okay, with our example, we can have r of s time, so here is s plus 2 over s plus 2 plus 0.3k, right? So here is the Laplace transform of the error. And let's say, okay, I want to know what happened to the error when t go to infinity. Okay, when t go to infinity, then what is the error? Yeah, go to what? Okay, so we can apply the final value theorem. Final value theorem. which say limit t tend to infinity of error of t equal to uh, limit s tend to 0 s time e of s. Okay. So yeah, we have I recall e of s equal to r of s time s plus 2 over s plus 2 plus 0.3k. Um, so from the final value theorem, yeah, four step input for step response. Step response means r of s equal to 1 over s unit step, right? And then from the final value theorem, e of infinity equal to limit s tend to 0 s time or 1 over s, which comes from r of s, and times s plus 2 over s plus 2 plus 0.3k. Okay. Then finally you have this cancel and s go to 0. Then you have 2 over 2 plus 0.3k. This is error with the response. Okay, with the okay, just say error of infinity.
Sir, it's 1 over s.
Yeah.
So why is it s times 1 over s and not just 1 over s as rs is 1 over s?
Because for the final value theorem say you must
Oh,
multiply s
s
here.
times. Okay,
Yeah.
thanks. Thanks.
Okay. So here, when k go to infinity, if you choose, okay, if you choose, let's say v, choose k tend to infinity, then you can have error tend to 0, right? So this is why this say crank up the gain, which means for some system you choose the higher the gain, the better the performance. Yeah, but in real life it's not always like that. There are always disturbance, noise, uncertainty of the model itself. So you can choose uh, some large number of page just to some extent. Okay, but anyway, here you can see that you can play around with the controller gain k such that you may achieve the desired output because the error tend to 0. And so okay, and next part. Okay, so next example, let me show another example. So the previous example, it's much like a model of DC motor, of a velocity model. Okay, velocity model, I can say, yeah, this first order. So this like velocity model. And for the next example, let's say we consider a position model. So from velocity, if you have velocity, then how you, what transfer function that you can have position. Oops, sorry, position here. So what is in between this? It is integrator, right? So the next example I'm going to show is that for the plane, we have uh, zero point 0.3 over. So first you have s plus 2 for velocity model, but then you have another integrator to have the position model. So here is position. Yeah, again you want to design too big a control again, k, right? Okay. um, then follow the same process first to find the characteristic equation. So the characteristic equation, G closed loop, G close is n over n, yeah, n over, sorry, k n over dn dos plus kn. Yes. So I can have 0.3k over, what is the, um, yeah, s square plus 2s and then plus 0.3k. So now for the system you have poles 1 minus 1 plus square root of 1 minus, yes, because delta prime is 1 minus zero point 0.3k, and then pole number 2 is minus 1 plus square root of 1 minus zero point 0.3k. And so from here we can see that if the value k um, is too high, then this part become complex number, complex conjugate, right? Pole 1 and 2 become complex conjugate. So the response, the step response would be, well, so here T. Step response in the case of damping ratio is greater than 1, you have step response like this. And then for higher damping ratio, which is close to 1, or even, or damping ratio equal to 1, you can have step response like this. But if um, damping ratio is less than 1, that cause that causes the pole to be complex conjugate, then you have the overshoot like this. Okay, maybe not so high like this. Okay, so uh, it the most important thing is that you have oscillation and overshoot, and then oscillation a little bit, and then how do I know that it convert to some value here? Again, we use final value theorem. Final value theorem, you have, well, yeah, for the error, okay, for final value theorem of, because this one is C of t, C of t. So first, we need to find C of s, that is equal G close time R of s. For step response again, RF is 1 over s, and G close is point 0.3k over s squared plus 2s plus zero point 0.3k. And again, applying the final value theorem, we time 1s, so s cancel with the 1 over s, right? And then 0.3k, and then s go to 0, so s square is 0 plus 2s also 0, and you have only 0.3k here. So 0.3k over 0.3k equal 1. So it means the response all converges to 1 here. Yeah, so 1 here is the one from the step. If you step to a certain number like 10, so this one is 10, and here you have a factor of 10, then this one just converge to 10 as well. Okay, so we don't need to care about other value, so just say the step is from 0 to 1, then we can obtain the position, the output, which is the position approaching to the reference, the step. All right. But anyway, what we can see, and in another point of view, is that if k grow too high, then we have too much oscillation in here. So oscillation can be even higher like this. But anyway, the system is always stable, given the fact that there's no disturbance, no uncertainty. But it's not the case for real life, right? Okay. But anyway, we when we know this property, we know how to play around with k to a certain range. Okay, now let me illustrate the poles with different value of k in the complex plane. Okay, and so poles and step response. So I put here set. So one side for step response here, step response, so C of t, and another side is root locus. So this one is complex plane, real number, imaginary number. Let me recall pole number 1 minus 1 plus square root of 1 minus zero point 0.3k, and another one p2 equal to minus 1 minus square root of 1 minus zero point 0.3 k. Um, so when k equal to 0, we have two poles, two real poles. Oh, no, I should keep like this, but I change this color. So the first pole is okay 0, and the second pole is minus 2. Okay. Actually, it is from this, right? From the open loop transfer function. This s equal to 0 is the first pole, and s equal to minus 2 is the second pole. And then I choose k a little, I increase k a little bit, all the way to up to a value that this equal to 0, right? I can say, if I say, well, 1 minus 0.3k less than 0, I can say k should be greater than 1, oops, so no, 1 over zero point 0.3, which is 3 something, right? Or I can say 10 over 3. Okay, so I increase k from 0 to 10 over 3, then uh, the value under the root, the square root, is still positive. Yeah, so we still get a real number. But we can see that because this close to 0, okay, then the two poles just approach each other, right? So the two poles just move too close to each other until, oh wait, it should be in the middle here, okay. Yeah, until k equal to 10 over 3, then these two poles become double roots, okay, double poles. um, then when k is larger than 10 over 3, these two poles become complex number, so they move, yeah, complex number, and they are complex conjugate. So if I have a pole, one pole here, I have another pole here, okay. And k go to infinity, then it's just go up, and this one is just go down like this, okay. uh, so now I link the poles uh, on the complex plane with the step response. So with the small k, small value of k, we have two real number of poles. Then the step response is like this, with real value of, okay, with real value of poles, we got damping ratio greater than 1, okay. And then for k equal to 10 over 3, we have critically damped, okay. This one is critically damped. And then for k greater than 10 over 3, we have under damped. Yes, like this. And if k is larger and larger, we have larger oscillation, right? We have like that. Is there any question? So how can you follow?
No, teacher.
No question or cannot follow?
No question for now.
Okay. So what else? All right. So if I look at the direction of the evolution of the rule locus, this one is clear that it go this way, and this one it go this way when k increase. So I hope you get some insight of what rule locus is all about, and you must be aware the how the step response looks like if you have rule locus in a different in one particular form. So it's, yeah, as long as you have the poles of the closed loop on the real axis, you have this kind of response. Okay, this kind of response. But when the pole just go uh, to become complex number, complex conjugate here or here, so the farther away from the real axis, the more oscillation, like this. Okay. And then what about rule locus for non-unity negative feedback system? So first let me introduce a non-unity negative feedback system. So you have a reference like this, and you have, yeah, you can put together the gain, controller gain, and the plant. And for the feedback, you have another transfer function like this. Okay, so this is called feedback transfer function. Okay, um, then you can find closed loop transfer function. TF means transfer function, uh, which say the input is R of S and the output is C of S. So inside here you get kg of S over 1 plus k g of S times h of S. Okay, just like that. So the characteristic equation would be characteristic equation 1 plus k g of S a of S equal to 0. And if you want to see the evolution of the rule of curves when k increase from 0 to infinity, then you just first map the pole and zero of G time H of S. Okay, pole zero. I say pole zero map of G of S times H of S. So this one is imaginary axis. This one is real axis. Okay, this one. Um, so you just multiply these two transfer functions together. So finally you have an s over ds, and then you can find zero and poles and just map here. If you got like for example 4 poles, just put it red. One pole here and a pole here and then a pole here, and its conjugate would be here. And if you have zero as well, let's say 0 is here and 0 is here, and then you need to sketch the evolution of the root, and then it is called root locus. So the next part of the lecture today will be the rules of sketching the root locus. Is there any question? Okay. um, okay, one more point that yeah, not yet, let me add. Yeah, one more point is that if you may ask, well, why we only consider controller with only gain k? Let's say I want to use other type of controller, for example, lead controller, lag controller, or PD controller, or PI controller. Okay, so for example, we have a control architecture like this, and let's say this one is PI. So PI controller would be K Kp plus Ki over S, and times our plan. Let's say we have the same system like before, which is 0.3 over S plus 2. Okay. So what can we do with this? How can we use the theory of root locus for controller design? So in this case, I reformulate the controller to be this form. So Kp is plus Kis is reformulated to be um, K K S plus Z over S. Where, so how can I know? Oh, what is the relationship between K with KPKI and Z with KPKI as well? So by um, okay, I think I can play around with this term. So I can have KPS plus ki over s equal to ks plus z over s. So if I have kp as a factor, then I have s plus ki over kp all over s. So this means k equal to kp, and oh, I can say this way. I want to say this way: kp is k, and ki is z times kp. Okay, because this ratio is z, so ki is z times kp. Okay, so what can we do with this form, and how we can apply the rule locus method? um, when we substitute this one in here, then we can rewrite the open loop transfer function. I mean the whole open loop transfer function with the controller part. So we can have like uh, k time point 0.3 s plus z over over s time s plus 2. Okay, so this is the equivalent transfer function, okay, for the open loop, for this one. Then we have the same structure to that structure that we can use rule locus to find the optimal value of k, okay, according to our desired output. But the difference is that right now we map the pole zero. Yeah, the pole zero map would be obtained from this transfer function, okay, but not from the original plant. Yes, only like this. So you can have two poles, first at 0 and -2 here, and you have 1 0. So how you get this 0? So in this process, in order to design controller using ruler curve method, which is to find k, you must choose z first. You choose by yourself. So if you are very familiar with the link between uh, poles, location, and step response, you know where to put z. Okay, you say, okay, maybe I put z here is good, or maybe I put z here so that I can have a good controller design. Yeah, good controller. I mean, a good controller for good performance. So maybe here, maybe here, right? So actually, as far as I know, 0 should be around here. Oh, no, no big deal. Just put here, no problem. Far away here. We we are able to find the right value of k so that we have good performance of the system. So anyway, we haven't come to the main part of sketching rule locus, but I want to give the insight of what can we do before we start sketching rule locus and find the best value of k when we want to choose different type of controller, which is not just a proportional with the gain k, okay, but can be your controller can be pi controller or lead controller or other controller. Okay. Oh. Is there any question?
No, it's okay.
Okay. So you can have a 15 minutes break. So we will resume our lecture at 15 past 9.